Good evening. So I will not be too long. I am really very happy to be here to celebrate Rafi's birthday. I came, as you may know, a long time ago in July 1990, so it's almost 30 years, 28 years. I came as a postdoc just after finishing my PhD in Liège. And when I came, life here was still quite different from what it was in Belgium at the time. Now, with globalization, everything looks more or less the same everywhere, but at the time it was different, and I really get a lot of help from Mira, from Rafi to adapt here, because that was not so trivial. And also, I want to thank Israel and Eva at the center, because it was really very nice and interesting for me to arrive in a different place, to do exciting science. And it is the beginning of a long story, because after a year and a half of postdoc, I came back to Belgium, I got a position, and I keep coming here and work with Rafi and to work on various subjects. So today I will talk about molecular logic. So it's a subject that is related a little to what we heard before and also to the talk of Sabre. As you probably all know, all our computers are built on the idea of a switch, and a switch is a very simple one input gate that can output either yes or a no, 0 or 1, depending if it is open or closed. And all what is done in our computers is to actually use switches. So, yeah, it's up. Switches that are connected in series or in parallels to implement a logic function, because it was demonstrated by Shannon that concatenating switches or switching algebra is equivalent to Boolean algebra, and therefore one can represent any Boolean logic function of any finite number of variables using switches in parallel and in series. And what I am showing here is just simple example of binary Boolean gates and AND gates, where you will get an output 1 when both inputs are 1, so you connect switches in series. And here, if you want an OR operation, which is to get an output 1 when either input is 1 and also when both inputs are 1, you connect switches in parallel. Now, the physical implementation of a switch is a transistor, and transistors are what is inside our computers, and they are rather sophisticated devices that are solid-state devices, and they have a switching rate of about a nanosecond, because this is the time scale for the dielectric response of the material when it is subjected to a voltage. So, in the late 90s, there were a field called molecular logic or molecular electronics, because chemists started to realize that actually a lot of molecules or molecules that are subjected to stimuli respond like a switch, and you can get a switching operation from a molecule with light by changing concentration, by inducing redox process, electron transfer, charge transfer. And so there were a lot of papers about switching. You change a concentration, you get a different color. And all of this actually amount to a sensing operation, since a sensor is a switch. The difference when Rafi started to look at the problem and the vision he introduces, that molecules are much better than a switch, because a switch is a simple yes or no operation, and as we heard a lot today, molecules can do much more than switches. You can control dynamics, and so if you are able to control dynamics, you can map the control dynamics of a system on complex parallel information processing. And moreover, if you are able to address the molecule in an ultra-fast way, that is with laser pulses, short laser pulses, femtosecond, now we have attosecond pulses, the information processing that is done by molecule will be much, much faster than the nanosecond timescale of our computers, than a gigahertz frequency clock. So this is the new approach that we have been working on, that we want to implement molecular computing or molecular logic that is grounded in dynamics. We want to know all the knowledge and all the way that we learned about how to control the dynamics of molecules, but we want to do so taking advantage of the atomic and the molecular scale that is inherent to molecules, and to nanosystems. So we want to use confined systems that have a discrete level structure. So we want to do molecular computing addressing the quantum states of the system. And this allows to depart from the switching paradigm because we can implement on this complex dynamics much more logic than just a switching operation. And so the basics of what we do is not to decompose logic function into switching. We also try to depart from the simple yes or no answer and to go to multi-valued logic all the way to continuous variable. And I will, in the next slide, show an example of a work with Itamar Wilner where we use biological system to implement continuous logic. Also with Sivan. I think Sivan was here, but she is not here anymore. And the last point that is important and novel in what we are doing in molecular computing is that we are not trying to only implement combinational gates. We also want to use a model that is called an automaton or a finite state machine. That is a model in computing where you have a logic unit and also a memory that is shown here, and your output is a function of both the input and the state in which is your memory. And this is a model that is very inherently applicable to a molecule because, as you probably know, the response of a molecule to a perturbation depends in which state it is. And so with this model, we have directly at the molecular level a hardware that is this kind of automaton and finite state machine. So with these ideas, the work started, and the first paper was showing combinational gates, a concept paper with Karl Kompa, who was mentioned before in 2001, where it is shown how to use laser pulses and photo excitation to implement simple and an OR gate. The principle is that here you are using two pulses with different wavelengths, and you will only access this electronic state of a kind of a dye molecule if the two photons are absorbed, while if you want to do an OR gate, that is to get an output whether one or the other or the two photons are present, you will have to use photons with comparable wavelengths. And you can do so because here we have always a broadening of the level, the first excited electronic state because of vibrational state. So it is possible to implement that scheme. And then we quickly went working with Uzi and all the knowledge that we had about high molecular Rydberg states and the dynamics of these Rydberg states to go and implement the two logic gates working in parallel and in such a way that they implement directly a half adder. And so you are photo-exciting here the electronic state of the NO molecule. You can excite it just below ionization and here to the visible optically bright state, and again using photon of different wavelengths, we can show that the dynamics of this system can be directly mapped to this logic operation, so adding two numbers, two binary numbers, and this scheme is already equivalent to 16 switches. And here we do not even try to have two gates. We know that the dynamics of the system is equivalent to this logic operation. And then you can do much more elaborated things. It is still the level of combinational logic. Here it's a work with Shammai Speiser from the Technion. We are using two dye molecules, rhodamine 6G and azulene, that are photoexcited to implement two concatenated half adder, which realize then a full addition. And this is equivalent to 32 switches. And again, here it is realized on two different molecules, directly mapped. And what is important is that we could show the cascade of information from one of the dye to the other, which correspond here to cascade the information between the first and the second half adder. And this is realized by energy transfer between the two systems. It is called a Foster coupling mechanism. I mean, the details do not matter, but we were able to show that using this principle, one can cascade information from one system to the other. Then it was the beginning of a very nice journey in molecular logic, and we started to be more ambitious, and we went to the EC, and we submitted project to a track that is called the FET Open track. So it stands for Future Emerging Technology, and it is called Open because you can come with your idea. It's a bottom-up scheme for having projects, so you don't answer a call, you come with an idea, and if the reviewer like it, they give you funding. It is also a very collaborative project, and the first one was called Molecular Molding Logic, and the subtitle here is to do molecular logic by electronic excitation and inter- and intramolecular quantum dynamics. And this is basically the motto of what we have been doing in logic since then. So after Molding Logic, of which Itamar was already a partner, I just show this to you because it is nice names and nice logo that we have each time to invent for the EC. So after Molding Logic in FP7, we had the project called MOLOC that is called, it was for molecular logic circuits. Then we had a project called MULTI for multi-valued parallel molecular logic. And of all these projects, in all these projects, we were collaborating with Itamar. Now we are in a project called COPAC for coherent optical parallel computing. Here we collaborate with Yossi Paltiel from the Hebrew University, but we have also in the partners, and it is thanks to Rafi Coriat, we have Elbit, which was mentioned before, who is in charge of preparing the real device, maybe, that will realize this optical parallel computing. So just to summarize, unlike what Sabre explained, we are using a classical approach, meaning that we are still using classical logic. We are not using quantum logic in processing the information, but we use in an essential way the quantum nature of confined system, because we use either the discrete level or different conformation states or different charge states. We provide input by a selective perturbation of the system, and the important point is that this perturbation will induce transition between the different states of the molecule, and we can use a various input. They can be optical, they can be electrical. In the work with Itamar, we are typically using chemical input, and the essential point is that the information processing is performed by the control quantum dynamics of this multi-level system. And of course, we need to provide, at some point, you need to route output, so we need to provide a probe of the system that will correspond to delivering outputs. So I am basically done. I just want to show an example of the work in collaboration with Itamar and Sivan from the MULTI project. This is a work that shows that we can use continuous logic to generate a polynomial that is a third-order polynomial, of which we control each of the coefficients of the different terms here, using a cascade of kinetic reaction between dianezyne and hairpins. So the principle here is to have a dianezyne that is able to self-assemble with an hairpin, and then the dianezyne has this cutting action. It regenerates the dianezyne we started from that gives us a feedback, so you get this model of an automaton or a finite state machine, but also provide an output that is the input for the next layer of reaction. And like this, we are getting concatenated automata that can be controlled by controlling the initial concentration, and that are equivalent to generate a polynomial of which we can control the different coefficients. And so this is an implementation of continuous logic, and the fact that we can go to continuous is kind of summarized here, and it is based on a theorem that I think Rafi likes a lot, that is called the Cox theorem, that says that we can associate a probability to each logic proposition. So the next example is a few words about COPAC, that is the project that is running now, because it has also connection to what we heard before. So from the experiment point of view, it consists in addressing a multi-layer of quantum dots that are semi-quantum dots with a sequence of laser pulses. So it is based on the dynamics of the nonlinear optical response of this. At some point, it will be a device of this multi-layer of quantum dots. And the nice points about these techniques is that using nonlinear optic and phase matching direction, one can measure simultaneously a lot of outputs. They actually correspond to the observable that we heard by Professor Tishby before, and one can measure them simultaneously at the macroscopic level directly. And so one can, adjusting the sequence of the laser pulses that are sent on this multi-layer, finally implement massively parallel logic operation, because we are using the algebraic structure that is underneath the dynamics, and in particular we are using the density matrix. We address in parallel simultaneously both the population and the coherence inside the system, so it corresponds to a kind of a molecular decision tree or a commutator tree between the observables and the dipole moment that govern the nonlinear optical response of the system. And what we can show and what we try to realize is that this control dynamics of the observables that is intrinsically parallel correspond to implement transform of logic function. And then we can read the coefficient of the transform directly at the macroscopic level on this 2D frequency response map. So I think it is basically time for the party. So I want to thank Rafi for his vision and also for leading us, me, colleagues, students, postdoc, through a lot of very exciting, novel, and stimulating paths in science. And I want again to say here, happy birthday. Sorry, I am not very good with those. Happy birthday, happy many returns, and many other projects and adventures in science. Thank you.